Hi, everyone. In case you haven't met me yet, or I haven't met you yet, my name is Julia, and I work on HNL searches, that is searches for heavy neutral leptons in IceCube. Thanks to the previous lectures we've had today, there is a lot of coverage on the basis of the theory behind it, so I'll just give us a brief review. And so to summarize, I'll kind of motivate why we're looking for HNLs, both with the theory and an overview of the current experimental status. Then I'll talk a bit about IceCube, the detector, and how we see HNLs in IceCube. And then we'll talk about our current status and future opportunities for the HNL search. So to start with the theoretical motivation, a lot of this was covered in our two excellent lectures this morning and right after lunch. But just to summarize, neutrino oscillations mean that neutrinos have mass. The smallness of their mass means that something funky is going on, and sterile neutrinos have been proposed as an explanation for this funky business. That being said, current experiments are in great tension with light sterile neutrinos, and this motivates the idea to start thinking about heavier right-handed neutrinos, which we call heavy neutral leptons. Once we're thinking about these heavy neutral leptons, we notice that through the seesaw mechanism, we can use them to explain the lightness of the active neutrino masses. And from there, we get creative and we start thinking that they could explain other issues like matter-antimatter asymmetry, some of the causes of dark matter, and even some of the oscillation anomalies. For example, in that top region of parameter space in our last talk, where you see that the gallium and reactor anomaly spaces start to converge if you emit some wave packet width. Those are kind of the 1 GeV ranges where HNLs start to become relevant. So there's a really good theoretical motivation to want to try to find these things. And of course, that means that a lot of people have already started to look. Now, when it comes to mixing with electron neutrinos and tau neutrinos, our limits are already pretty strong, as you can see up here. And in fact, below 0.5 GeV, the parameter space for HNLs is pretty much completely ruled out. However, as you get to higher energies, and especially as you start looking at the mixing with the tau, there's much more room in this parameter space that is yet unexplored. So we haven't found HNLs in this region, but we haven't expected to see them either. Part of the reason that our tau mixing is so unrestricted so far is because of the difficulty in seeing tau neutrinos in a lot of current experiments. And this is really where the power of IceCube is. So we're trying to design our analysis to have a sensitivity region around this kind of cyan oval, but the exact parameter space is a work in progress. So why is IceCube so good at seeing tau neutrinos in the first place? Well, we have an advantage, and that's that we get this excellent atmospheric muon neutrino flux, which as it traverses the Earth can oscillate to tau neutrinos. And this means that we get more tau neutrino events than any other experiment in existence. We expect around 2.5 thousand events in 10 years. And so we're able to put limits on tau neutrino mixing that other experiments are not. And the way this works is a neutrino is going to enter the detector and interact with the ice. Charged secondary particles are going to release Cherenkov radiation, and our DOMs are going to pick those up, the digital optical modules. In deep core in particular, the DOMs are much more densely packed, and so that's going to give us a better spatial resolution and therefore greater sensitivity for BSM searches. The events we can see in IceCube range from the several GeV to high TeV scales. And so when we're looking for HNLs in the GeV range, this is considered a very, very, very low energy event on the scale of events that we find in IceCube. So what do low energies look like when we see them? Well, we can divide them into three kinds of event topologies. We have track-like events, cascade-like events, and double cascade-like events. Track-like events are often muons. They just kind of go through, they deposit energy relatively uniformly. And as you can see, this like pink dot, oh, I am pressing the wrong thing. This kind of pink dot shows the direction of our particle. They kind of go straight through. Cascades happen when you have neutrinos depositing all of their energy kind of in one spot. And double cascades happen where you have an initial energy deposition, then a longer lived particle, and a second energy deposition over here. This distinctive double cascade shape pretty much only appears in tau neutrino interactions. And when it happens, if it happens at these low energies, it's going to be a clear hallmark of an HNL signal because there's no other process that we know of that can produce this distinct topology. So how exactly does this happen? Well, step one is that the tau neutrino is going to pass through the detector and it's going to scatter off an ice nucleus, producing this first cascade. Then the HNL will travel some distance and decay, releasing a tau, which gives us the second cascade, and a hadron, and other particles also producing light. So you have these two cascades, and then we have a distinctive decay length between them. Now, the decay length is going to be determined by the mass of the HNL, its energy, its mixing with the tau. And because IceCube is constructed to be the size it is, with the spacing of the DOMs the way they are, and the time resolution that we have, we actually are only going to be able to search in a very particular region of parameter space, where the decay lengths are down to a centimeter if we can make our reconstruction really, really, really good, and up to the size of our detector if we get incredibly lucky and our first cascade is on one edge and our second cascade is on the other. But what this really means is that here is our sweet spot region, and we're going to be most sensitive to mixings above 10 to the negative fourth. And that's where you start to get the region of things that have already been ruled out by current experiments. However, the higher you push the energy of the HNL, or the lower you push the mass, the shorter these decay lengths are going to be, but the lower mixings you can observe. And so our sweet spot in this higher mixing, higher mass parameter space is where we're going to have the greatest opportunity to be sensitive in our double cascade search. But why limit ourselves to a double cascade search? There are a lot of problems with that. Few of our HNL events are expected to be resolvable as cascades. Background events can mimic signal events. If you have two backgrounds that happen to be time coincident, and low light from the first cascade can actually cause double cascades to be misidentified, usually as single cascade events. Furthermore, reconstruction of the decay length is a work in progress. And at our last attempt, there was only a 25% correlation between our true and reconstructed decay length. But hope is not lost. We can actually reframe our analysis to take two parallel paths where we sort our events into cascade-like, track-like, and double cascade-like events. And so we take our three event topologies like we had before, and our cascade-like events can go quite nicely into this cascade-like bin. Our track-like events go into the more track-like bin and then get discarded because those are the ones that we're very confident are not HNLs. And then our double cascade-like events sometimes are misreconstructed as single cascades and sometimes might be faithfully reconstructed as double cascades. And so what we can do is we can double our analysis. We do one analysis where we have a cascade-like sensitivity, and we have some preliminary sensitivity curves here, where this is the signal over square root of background for a sample mixing angle and two sample masses. We see that the tau mixing with the HNL and the greater the mass of the HNL will actually be able to see kind of an excess in our expected cascade-like events. And so even if we can't resolve any double cascades at all, we can still see a change in the shape of our single cascade signal and create a sensitivity by looking at these excess events. By doubling this and using our double cascade events also, we can combine these two parallel tracks to get a greater sensitivity for HNL events overall. What this is going to require is a dedicated heavy neutral lepton simulation, which is currently being refined. And we're going to have to switch from using the typical IceCube low energy event reconstruction for the IceCube people in the room. That's the OSNext reconstruction that we've been using, and move towards a reconstruction that is actually built to look for two cascades, which is currently not the case. With this tailored simulation and reconstruction, we will be able to determine our sensitivity to double cascade events. So this sensitivity should be out within the next 3 to 6 months. Thank you guys so much for listening, and thank you all for attending, and to the organizers. In particular, thank you to Leander Fisher, Summer Blott, and Carlos Arguelles Delgado, who form with me the rest of the HNL search team.
Thank you, Julia. Questions? I actually have a question. So when you talk about double cascades, you really mean two cascades which are separated. You can also look for these double waveforms, yeah? So basically the waveform signals which is slightly separated in the optical modules. Is this something that you could use?
Yeah, so we actually have, I have a summer student working with me this summer who is working on trying to determine whether our time resolution in the DOMs is going to be good enough. But because at these low energies, the DOMs currently actually don't save waveform information, that's something that would have to wait for the upgrade. And we would not only have to wait for the upgrade, but actually convince the collaboration that it's worth saving this DOM by DOM waveform information. So yeah, if you'd like to help encourage that, I'd appreciate it.
Thank you.
Thanks for the really nice talk. So what you're saying that at lower energy, if we observe two distinct bursts of light, so it might be a smoking gun signature for the HNL?
Yeah.
And so what would happen at higher energies? Because once the taus could travel an appreciable distance, would there be a misclassification between HNL and taus?
It's highly unlikely. And the reason for that is that the higher energy an HNL has, and especially the higher mass it is, the shorter the decay length. And so if you have a very high energy, high mass HNL, it's likely that these two cascades will be very close together. Whereas for the high energy taus, and also we're talking about several orders of magnitude separation, like these events are between 0.1 and 10 GeV at its widest range, whereas the astro tau events are like PeV scale. So it's highly unlikely that you would see a coincidence of those two parameter spaces. So we're not really worried about it.
All right, thanks.
Any other questions? Yeah.
Yeah, thank you very much for the nice talk. Yeah, I would like to ask you, how would this HNL affect, for example, the tau neutrino or the tau propagation in the Earth? Have you considered that?
Yeah, so in the Earth, taus would be able to upscatter to HNLs like you would here. Mm-hmm. The mixings that we're considering are pretty low. Mm-hmm. And so especially because the oscillation tends to happen only partway through the Earth, it probably would not cause a significant decrease in the tau events. But if we get to, let's say like 10 to the -8th sensitivity in our tau counts, at that point, it could have an effect. We're not there yet though. So at this point, we wouldn't be able to see it.
Thank you.
Okay, if there are no further questions, let's thank Julia again.